Hey there, how is everybody doing tonight? Awesome. Everybody knows me, but I'll tell you anyway because we have an audience that's watching us. My name is Mark D'Antonio. I'm the Chief Photo and Video Analyst for the Mutual UFO Network. I also run the SkyTour LiveStream, which is out of the John Zach Memorial Observatory in northwestern Connecticut. I usually say picturesque northwestern Connecticut. And we bring the deep night sky to people all over the world who wish to join us in the night. And it's really a fun time. Come join us. Go to the YouTube channel, SkyTour LiveStream with Mark D'Antonio. Subscribe, click the bell to be notified, and really have a good time with us. And we have a really fun time there. And also, a second site that's wonderful is P&K Space Imaging, run by Paul and Keith. These guys show you the moon and planets like no other. And I am affiliated with them. They're affiliated with me. And yes, we're patting each other on the back, okay, because this is the way we want to present astronomy. This is public outreach at its best, folks. So join us there if you would. Also, Bill New York Skywatcher, who is hosting this wonderful party here for us, and this is a wonderful venue. It's an outdoor site. We're having fun. We've got a lot of people here. They're all out in the audience. There's tons of people here. There's probably 4 million people here. Okay, you can hear 2 or 3 of them laughing. But that said, I wanted to bring you a talk tonight, which is called Exoplanets and Alien Life. Now, what would that be about? Well, Exoplanets and Alien Life is a talk that deals with our place in the universe and our planet, and we talk about where we come from in terms of, how the Earth might have developed here, and then we kind of project that outward to see how we might have actually where we might have come from or what other life might exist elsewhere. So we go to the next slide. Okay, now we're a lonely speck of dust in the universe, or as my friend, well, not my friend, but as Carl Sagan, an astronomer that I grew up with, listening to him on all his television shows, including Cosmos, the original Cosmos series, as he used to say, we are a pale blue dot. And that is exactly what he used to say. And I used to love that phrase. I didn't know what it meant, because I was little at the time. But as time went on, I began to realize we are a pale blue dot. And as I looked at our pale blue dot, our Earth, I often wondered, is it possible that our planet has been visited before by an alien civilization, that is an advanced alien civilization? I don't know if that's true. I don't know if it's possible, but I do believe it. And, could someone find us? And, do we think it might have happened before? Okay, and we do think it's happened before, but there's no real tangible evidence. But there's plenty of circumstantial evidence, and one of the things that I think is important to think about are some of the stories and myths that we have seen in our history. So one of those is the myth of the Wandjina. Now the Wandjina were, and just one case, the Wandjina were a race said to come from the stars, live in the oceans, and have mastery over the water. This is something that I think is an interesting story. It's an interesting myth. But there's something to it that has a little funky twist, a little bit of a twist that I think is cool. And one of them is that, according to the myth, 2 boys were torturing an owl to death. And the Wandjina, who lived in the water, took revenge on the Aborigines. This was in the Kimberley region of Australia, like 5,000 years ago. So this was a long time ago. And so we have to say, was it an owl or was it a gray alien? There's a lot of stories that talk about owls looking like aliens, aliens looking like owls. Maybe they're just owls. It's very possible. But you know what? We do have to consider this other possibility that maybe we were looking at aliens. Maybe that's what they were torturing. Maybe they tortured an alien to death. Don't know. But, for us, we have to find out. We want to have a reason to look for life elsewhere, and we do have some legitimate reasons, okay, to wonder if we've ever been found, okay. And one thing we can do, which we expect that an alien life form might do, is to look for life like us out there. An alien race might look for life like themselves. This is something that I think is important. It's something I think that we are doing. We are, okay? And when we look at, Earth-like, we have to ask, what does Earth-like mean? All right, well, Earth-like means a habitable zone. It also means liquid water on the surface. It also means having a stable star system. We have all three. Now, some recent developments have shown us that our planet may not be the most habitable planet to be on. You might say, well, we're living here. How could that be? Yeah, we are living here. We have earthquakes. We have tornadoes. We have volcanic eruptions, as we've seen in Kilauea lately. All right? And we have weather that can be very deadly to us, smog and so forth. We also have ultraviolet rays that come from the sun, our star. And those rays can kill us. So that means we're a habitable planet, but are we the most habitable? Some scientists feel we're not. And that a planet that can support life better than us is a planet that's super habitable. And super habitability is something that we'll talk about. Now, on June 9th, we're going to see June 9th, 2018. That's coming up. We're going to do a presentation at Pine Bush. The Pine Bush presentations for this weekend were called off on the account of the fact that we had violent weather here. And violent weather, I am in New York with these folks here, violent weather called off the presentations. But we are doing it anyway because we're diehards. And we have a lot of people here that want to see it. So, super habitability is something we'll address at Pine Bush even more so than here, because the presentation will be a little bit differently done on June 9th, okay? So, habitable means these three things: a habitable zone, liquid water, and a stable star system. That's life as we know it can survive there. So, what does a habitable zone mean? Okay? A habitable zone is that location around the star where liquid water can form. That's something that is something, it's somewhat unique to this planet. We're right at that place where liquid water can exist on the surface in pools, the ocean, right? And in lakes within our country, other countries all over the world. And in the ice sheets as frozen ice, but it does melt from time to time, as we see with climate change causing the melt, all right? So moving forward now, we have to say, what about that liquid water? Well, it's dictated by where we are around the star. We are in that right place, 93 million miles from our sun. That's one astronomical unit. And at that distance, this gives us the opportunity to have this liquid water on our surface. Venus is just on the inside edge of the habitable zone for our planet. Mars is just on the outside edge of the habitable zone for our planet. Mars is a little too cold, can't have liquid water on the surface, and that has to do with a lot of reasons. Venus is too hot. Its atmosphere is 90 times the density of our own. But guess what? Our atmosphere used to be 90 times denser, just about. But because we're in the habitable zone, something else could happen here that couldn't happen at Venus. And that was rain. Because we have the ability to have liquid water on our surface because it's not too hot, and the water molecules don't get disassociated when they're in the atmosphere by ultraviolet light from the sun, we actually were able to have liquid water rain on our planet. Venus never had that ability. So when H2O that Venus did have ever got into the atmosphere and got higher in the atmosphere, the ultraviolet light from the sun could penetrate the atmosphere for a reason I'll tell you in a minute, and take those H2, the two hydrogen molecules and the one oxygen molecule that make up water, split them apart, leaving the oxygen, which would bind with stuff in the ground, other elements in the ground to make, like if it bonded with iron, it would become iron oxide, and it would make these oxides and would oxidize anything it came in contact with, and leave the atmosphere pretty quickly. All right, the hydrogen would be lost to space. All right, so the reason that happened is because Venus doesn't have something else that is vital to life on a planet, and that is a magnetic field. Our planet has a molten outer core and a solid inner core. That molten outer core in our planet moves around against that inner core. This generates huge electric fields, which in turn generates a massive magnetic field. And that massive magnetic field is what protects our planet. You've all heard of the Van Allen radiation belts. They're around our planet, and there's all kinds of people that say, well, the Van Allen radiation belts, basically encase our planet in deadly radiation. Yes, at times that's true, but the Van Allen radiation belts are also penetrable. We can go into them if we go out through the top, where they're the narrowest, and we have when we went to the moon, and we did go to the moon. So that said, when we talk about these radiation belts, the Van Allen radiation belts are actually the result of particles from the sun, high-energy particles, that are trapped by the Earth's magnetic field. And thus, those become the Van Allen radiation belts. All right? And we do have a jet going over. It's going over about 600 feet. A little low. We had to duck, However, that said, the Van Allen radiation belts are also responsible for keeping us alive, because the high-energy particles that come from the sun hit those, and they're forced to spiral around the pole, and the Antarctic pole and the Arctic pole, and they spiral down in the atmosphere. And when they do, we see something beautiful. It's the Aurora Borealis at the North Pole and the Aurora Australis at the South Pole. And those are the northern and southern lights. And so that's the result of the interaction of high-energy particles with our atmosphere. Very interesting stuff. And Venus, of course, doesn't have that, because Venus does not have a magnetic field, not at all like the Earth has. That's something that I think is important to follow and understand. And I think that it's something that that as we move forward, you get an appreciation for. Okay, so that said, moving along, if we talk about our sun now, and in terms of stability, our sun is actually a pretty stable star. And when we talk about how some stars act, some stars have these flares. M stars are the most prolific common star in the entire universe. There's more M stars in our galaxy than any other kind of star. What's an M star? It's a very cool, as in neato, yeah, far out and cool, but it's also very low temperature. And an M star might be only about 3,000 Kelvin, say, or 3,500 Kelvin, which is a temperature range. And at 3,500 Kelvin compared to the sun's 6,000 Kelvin, all right, we're talking about a vast difference in temperature. And when they're cooler, they're also redder. Now, the thing is, they're also small. And an M star might only be 1% of the size of the sun, or have 1% of the output of the sun. Very, very small star. And so, as such, the habitable zone, where you might have liquid water on the surface, might be a lot closer, will necessarily be a lot closer to that star. And if it's a lot closer to the star, we're also going to have another situation. We're going to have a planet that might actually have a year, like we have 365 days it takes us to go around the sun, but a planet that's in the habitable zone of one of these M stars might have a year that's only like 10 days long. That's pretty cool. And if it's very close to the star, it also might be locked with one face of the planet facing the star as it orbits the star. That's called tidal locking, and our moon is tidally locked to our planet Earth. That's why we see the same face. The moon does rotate once a month, but it does it in a way that's synchronized to the rotation around the Earth. As it orbits the Earth, it completes one spin on its own axis for the time it takes it to go around the Earth once. And that's pretty cool. That's why we see the same face. We don't ever see a different face of the moon. So, that said, these stars, like the M stars, one of the problems they have is that they're not as stable. Not as stable as a star like our sun, but they are the most prominent, the most prolific, the largest population in all the galaxies. So when you look up at night, at the darkest location on this planet, and you look at the thousands of stars you can see in the sky, not one of them is an M star that you're looking at, because none of these M stars are visible to your eye. They're all too faint. In our SkyTour LiveStream, we often go to these M stars, and you can actually see they're very bright red stars, but you can't see them unless you're looking through a telescope. And when you look through a telescope, there they be. And they're bright red. You can't mistake them. And I know that people have come and seen this. Those of you listening and watching, you have actually seen M stars and what are called carbon stars, another type of M star that we've shown in the SkyTour LiveStream. Now, so M stars, although populous and most populous in the whole galaxy, they're also not visible to your eye. So we want to ask, well, what kind of stars are there? I'm talking to you about M stars. Well, what M star? What's that mean? Well, let's show you. Can they support all planets and life? Well, not all of them. So moving along to the next, this is a diagram that I created called the Hertzsprung-Russell Diagram. It's actually a recreation of a diagram created by Ejnar Hertzsprung and Henry Norris Russell, okay, which actually describes how stars are categorized. Now, across the bottom, we have these capital letters. Now, that's called the spectral class. Highest temperature is to the left. Lowest temperature is to the right. Notice what's to the far right. M, what we're talking about. O stars are the hottest and biggest stars, the most massive. They're also the most short-lived. Okay, Alnitak, the leftmost star in Orion's belt, it's only going to be here for a few more million years perhaps, and then it's going to explode in what's called a supernova. And all of the elements that it's creating in its core that belong in our periodic table, as you'll see shortly, will be released to the interstellar medium to be used to make other stars somewhere else and other planets possibly. Okay, and in the middle you'll see there's G, kind of near the end, and that's us. We're a G. We're actually a G2. Within each of those spectral classes, we have a 0 through 9 designation. So we have a G2, and we are a star that is right where the sun, it says sun, right there. And that's us. Okay, we're right there in the middle. Now, you can see that there's also supergiants. Some of those stars are so big that if you put them where the sun is, their size, their outer diameter would take them out past the orbit of Jupiter. That's big. And those are some stars out there. There are stars out there of that size. Moving on now, we have to say, well, what's the consensus for where planets can exist? O stars don't last long enough. B stars may not last long enough, but we know that it's possible. So we think that starting with A, being safe, starting with type A stars, all the way down to M, we think we can find some planets that could be habitable long term. So A stars are hotter, as you can see, left is hotter, and F stars are hotter by a little bit. But A stars being hotter are stars that would actually have a habitable zone that's farther away from the star than 93 million miles, which is what we are at. We're sitting 93 million miles away. If we were 93 million miles from an A-type star, we'd be fried. We'd have to be a lot farther out, probably farther even than Mars, okay, in order to be in the habitable zone. And that would mean that our year would be that much longer because it would be a slower orbit the farther out we go. So maybe our year might be 450 years, or not 450 years, so like 450 days, okay, as opposed to, say, 365 or, some other number that makes more sense for a distance out past Mars, say. Depends on the mass of the star. Anyway, moving along. Okay, this is, we remember this from chemistry class. We hated it. We never liked to consider the periodic table of the elements. But what's important about it is these colors. You'll see that most of the locations on this periodic table have a color code. That color code is something that is very important because it shows us where these are created in the universe. Our periodic table wasn't created in a laboratory. You see, all of you here and everyone listening and watching were made from elements that were first synthesized in the core of a star somewhere else. See that? So when Carl Sagan said, "We are made of star stuff," he wasn't kidding. We really were. And that's what this is all about. So you'll see that exploding massive stars, like that star I told you before, Alnitak, the leftmost star in Orion's belt. When that blows up, we might get aluminum, silicon, phosphorus, sulfur, chlorine, argon, and some of the other elements all the way down to bromine and krypton. Krypton there. This stuff that we get there, that's something that we will actually see coming from these supermassive stars. All right, and that's how it works. The universe creates these in the hearts of stars. When the stars blow up, they're released to the ISM, the interstellar medium. We call it the ISM, and those would end up populating the nebulae that make up new stars and new planets. So planets elsewhere and stars elsewhere would be formed with these elements. Our sun has elements in its solar atmosphere that just can't be made in our sun. Our sun's not massive enough to make magnesium, for instance. Okay? But it's there. Why? Because it was formed with it in the beginning. All right? So this gives you an idea. So this is our periodic table, and it comes from the varieties of interactions out there in the universe. Now, how do we find these planets? One of the things we do is we build satellites. This is the Kepler Space Telescope, and it was launched in March of 2009. And when it went up, it was actually very, very successful. And it has a curved sensor on it like this because we've noticed early on that different color lights focus at different locations on our sensors. And if you had a flat sensor and a curved lens, when the light comes through, the light going down to the center is perfectly focused, but you see it's a longer distance for the light over here that's going to focus. So the light near the edges would focus at a different place. So we make the sensor curved to actually account for that, so the light actually hits at the same relative place. Okay, and that's something called Petzval radius curve. Oops, you went too far. It accounts for Petzval field curvature, it's called. And this is a little aside. This is just kind of a neat little thing. And so it was designed to have a perfect focus in this way. Now we go next. And so the Kepler Space Telescope is a very interesting system because to keep it orbiting and to keep it actually oriented on a particular star, because it's very, very sensitively placed because of what it does, as we'll see shortly. To keep it placed, it has a series of what are called reaction wheels. What are those? Well, they're wheels that actually are spinning, and there's 4 of them. And they're canted at angles to each other, and that cant is responsible for generating a torque on the system. So when they want to move the telescope in any particular direction, they spin these wheels a certain way, and it will move the telescope because it induces a torque or a force, which can twist, rotate, and pitch, and all that. Okay, and that will put the telescope into a certain orientation. Next, so and there's a close-up of the reaction wheel. There's 2 there. I took these photos actually out in Arizona when another satellite was being built. I was there working on a project to create these very high-end engineering models of the satellite. And when I did, this is I took this picture. You can see the reaction wheels right there, but I'll show you the next one. There's actually a close-up. So here you see them. And buried inside there, this is before all the protective foil is put over them, all of them, because these are internal components that get covered later. So the reaction wheels are put at this angle, okay? Next. Now that's me in the bunny suit. Now, why did they put me in a bunny suit? Well, no, not just to prove I was there. To show you, though, this cable, this braided cable, all right? Satellites, when they put up satellites, it's a very serious business. And if there's any problems with static electricity being translated or moved over and that goes to the satellite in any way that's being worked on, you could blow it out. And it might never be found out until you get in orbit. So, tens of millions of dollars later when it's up in orbit, you say, oh, it doesn't work. What happened? I don't know. You don't have room for that. There's no room for that, let me tell you. So that's why this braid, whenever you get within 3 feet of the satellite, you plug in that braid. There's an alligator clip at the bottom, all right? You plug in that braid into a rail. It wicks away all the electricity from your body, all the static charge, and then you can come within 3 feet. Now, when I was working on this project, there was one fella, unlucky fella, that actually got within 3 feet of the satellite who had not put his braid onto the rail, and he was summarily fired. And I was like, wow. Now, they're very serious about this. You put your foot in a device that actually literally sucks your foot off. It feels like you're taking your foot off. It pulls all the dirt and everything out of your shoes. It's a real expensive cleaner for shoes. I mean, it does a great job, too. It's like, wow, my shoes never look so clean, okay? And it just pulls all the dirt and everything off your shoes. And then after that, you put booties over your shoes and then booties over those. Do you see what I mean? They're serious about getting nothing in there. And then I came in with my camera. My camera, of course, had to be thoroughly vetted and taken care of. But anyway, it's a serious business, and there's no room for error. Now, when we talk about how Kepler works, what it does when it's up in space, it looks for these. It looks for what are called transits. If there is a star out there, and it has planets around it, if those planets come along the line of sight of the Earth and the star, and they enter the face of the star as seen from here, then there's a tiny, and I mean minuscule, drop in the star's light as the planet crosses in front. Then the bottom of the curve gets flat if the whole planet's on there, and then it starts to come up again as it goes off. And the speed at which it enters, the speed at which it comes off, that slope, the way that's shaped, tells us about how big the planet can be, how fast it's moving, and tells us a lot of factors. And we can actually determine the size of the planet, the mass of the planet in some cases, if we know the star. And there's a lot we can do with this information. That's what Kepler does. So Kepler looked at over 100,000 stars initially, and that was the initial Kepler mission. Now, what's 100,000 stars, and how big is that? Well, that's the constellation of Cygnus, where it's looking. It's an area a little bit smaller than your fist extended at full length in the summer sky up over your head. It's a little bit smaller than that. And within there, to date, we have about 3,800 plus exoplanets, a good number of which are somewhat Earth-like. In just that little tiny space over our head. That's not bad. Think about how many of those fist-sized areas there are in the universe. If you move around, that's just in our galaxy. All right? So, we found nearly 2,000 exoplanets initially, and that number has since gone up to nearly 4,000. So, there are other methods to finding exoplanets, and in fact, they're very important. We can't just use transits. Transits aren't enough. We have to have ways to confirm what we're seeing. It's confirming what we're seeing. All right? This is very important. All right? And to confirm it, we have other methods, and one of them is radial velocity. All right? When you see when in sound in an atmosphere with air, sound waves, as they approach, they increase in pitch. You hear, and as it goes by, it's like, yo. Okay, well, that, came to be known as something called the Doppler Shift. All right? And that Doppler Shift occurs with sound on Earth, with sound waves that are generated, a compression wave generated in the air. But with light, you also get the Doppler Shift. And that is when a star is coming towards you, like the star there coming toward us, the light is shifted toward a higher energy part of the spectrum. It looks bluer. All right? We see the light. It's called blue shifted light. Then as the star is going away from us, it's red shifted light. So we have blue shift, red shift, blue shift, red shift. Okay, or in your case, blue shift, red shift, blue shift, red shift. So that's something that is very important and something that we use to actually confirm what we're seeing. All right, and if we get a transit, we use the Doppler. We use this, radial velocity. It's called. We measure the shift, and that tells us the velocity of the star coming toward us and away from us, and that gives us an idea of whether it's moving. Now, why would it move at all? Well, stars move through space, yes. But if they have planets around them, see the unseen planet right here? Now, if as a planet's going around the star like that, as a planet goes around the star and the planet are in a dance. The star is kind of going like this. It's wobbling as it goes through space because as the planet goes around it, it's tugging on it a little. So as it goes around it, the star is going to do a little dance as the planet pulls on it because they're orbiting a common center. All right? Now, the planet's very low mass compared to the star, so that wobble is tiny. In fact, the common center of rotation between them probably is within the diameter of the star itself, which we can't see. But we see what it does to the light, and that's what's important. The Doppler shift of the light, and that gives us the velocity of that movement. That velocity of that movement tells us about the planet, all right, and helps us confirm that it's a planet. Now, you can think, well, if the star is if the plane of that solar system this star is in is edge on to us like this, okay, then we get a very accurate radial velocity because then it's coming directly at us and directly away from us. But what if it's like this? Well, then it's coming at us a little bit here and going at us, going away from us a little bit there. We're not seeing the exact thing because the plane of its solar system is on a weird angle. And if it's like this, then we don't see anything at all because the star's not coming at us at all. It's just circulating this way. And we can't hope to see that too well, especially if the star is any distance away. So radial velocity is one method that we use. Another method is direct imaging. All right, this is a case. This actually, Peter Michaud at the Gemini telescope. I asked him some years back for permission to use this image. This is the first directly imaged other star system with planets ever seen. Okay, and this was. You can see the circled planets there. No, that's not a black hole in the center. That's actually called an occulting disk. It's used to block out the glare of the star. Why? Because if that wasn't there, the glare from this star would totally envelop everything in this image. all right, and we'd never see the planets. The occulting disk is used to block out the glare of the star, all right. That leaves behind something that we can see. This was actually seen in the infrared. So this is what's called excess infrared, meaning heat, all right. It's the first directly image of a star system. Another way is to actually try to do astrometric measurements. What's that? Remember I told you about this? A star that's like in this plane, like that's toward us here. We're not able to tell, if it's coming toward us or away from us. Well, that motion like this is something that if the star is near us, we can actually detect that. We can see if it's close to us, we can see a little wobble as the planet's going around it, and the star and the planet are going around each other, and they kind of, the star gets pulled toward the planet a little bit, and as the planet goes around, the star ends up overall looking like this, doing this little wobble. If it's close enough, we can detect that wobble. All right, and that's what we see here. This image here, complicated as it is, shows us the sun's wobble. There's a yellow ring right here. This is the diameter of the sun. And you can see that the sun's wobble, most of that wobble's inside the sun. That is to say, you don't see anything outwardly from the sun moving because that wobble and motion through space of the sun is contained within the sun itself because there's so little. This is due to all the force of all the planets tugging on the sun. There is a little bit to the outside, okay, due to Jupiter and so forth. And that's what's really important to look at. We can see that. We can detect that minute wobble if the star is close enough to us. So that's what we're talking about here, okay? Now, another method is something called gravitational lensing. This one is the one that's craziest of all, I think. Because if you have a star here and a planet going around the star like this, and a much farther star, farther away, if the planet going around that star gets anywhere near the more distant star, then that distant star's light is going to be changed by the gravity of the planet that's passing through that area. It makes what's called a gravitational lens. It's the coolest thing because you can actually watch this star change its shape from a round object to a kind of a ring or a partial ring as the gravity affects that gravity of the planet affects that distant starlight. And that's gravitational lensing. We've seen it. And there's simulators out there you can download even for your iPhone to look at a gravitational lens and simulate it based on different masses. Really cool stuff. Now, if you're interested in exoplanets, then one of the places you can go is the Open Exoplanet Catalog. It's online, it's free, and you can go see all the latest exoplanet finds. Now, if you have an iPhone, you can go to this next thing. All right, and this next thing, thank you. This next thing is an application created by Hanno Rain, okay? And Hanno created this wonderful application called Exoplanet, and this is for your iPhone. This gives you an example. In fact, you can see the first ones there show us the TRAPPIST system. Now, I marked some of them as favorites for the ones that I think are in the habitable zone. And these are, this is a really good compendium. This is a direct mirror of the Open Exoplanet Catalog that's online. So if you're not near your computer and you happen to be driving from one place to another, hey, just pick up your phone and go to the Exoplanet Catalog and just hang out in there for a while you're driving. No, wait, no, don't do that. Wait until you get there, okay, and then do it. So you probably don't want to do that while you're driving. Thanks. Now, when you talk about the Kepler Space Telescope, what I didn't mention is that the Kepler Space Telescope as a space telescope went down. Remember those control wheels, those reaction wheels I was telling you about? Well, the Kepler Space Telescope can operate on 3, and it had 4, but it lost 2. So that meant that now it could no longer be accurately pointed. They could swing it this way, but when they went to swing it that way, there was no force that the remaining reaction wheels could impart that would cause it to actually go up or down, for instance. And so that was a problem. So what did they do? How'd they fix that? Well, some engineers decided, the sun has energy that it's putting out, radiation, pressure, energy, high energy particles. They calculated the force of those high energy particles hitting the Kepler Space Telescope. And they figured, hey, we'll let those be the force. That's the other reaction wheel that's missing, and we'll just tune every other reaction wheel that's remaining, the other two, to the force of the sun. And they had Kepler back. And that became the rejuvenated mission of Kepler called K2. And we can see that the K2 candidates are just a huge number. Look at, as of January of 2015, all those blue dots are new objects, new candidates for exoplanets. In July of 2015, just a few months later, we had all these additional yellow ones that were confirmed. That's a total of 4,696 objects that have been added to this list of Kepler, objects of interest or Kepler candidates. This is incredible. So, an additional way that we find exoplanets is using the Spitzer Space Telescope. Spitzer was launched in 2003, and it had a 2.8 foot diameter mirror. Now, what limits what we can launch into space? The diameter of the rocket that can launch it, right? We can't put anything in that's bigger than the diameter of the rocket. Now, we've seen SpaceX launch things that are a little bigger than the diameter because they add this bulbous dome over the top, okay, this aero shield, right? And that actually protects larger payloads. But we can't put up anything really big. But we have a method. So the we can right. Okay. When we're trying to find, what the Spitzer Space Telescope did was it actually tried to find or look for the atmospheres of these exoplanets. Now it's you have to understand, these are not large objects. We're looking at things that are sometimes 10 to 20 times smaller than the star itself. And we can't even see the disk of the stars themselves with our telescopes. We can only see the effect that the planets have on the light. But check this out. If this is the curve of the star, and a planet is moving on to the star in transit, moving across the face, as seen from the Earth, okay, through the curve, just as it enters the star, the first thing that enters the star is the atmosphere of the exoplanet, if it's there. And we can see for a moment that contamination of the star's spectrum with this little tiny bit from the planet that's coming on. Then once it gets on, the same thing happens as it gets off over here. We see that contamination, and we actually can then calculate and figure out what is in this atmosphere. We're trying to do that with the Spitzer, but again, okay, the Spitzer Space Telescope's mirror is only 2.8 feet in size. Go ahead. All right, and the James Webb Telescope, which is going to go up next year, they keep adding the years. It's like next year they'll probably say, okay, 2021 or whatever, or 2020. So the Spitzer has a 21-foot. I'm sorry, the James Webb Telescope will have a 21-foot mirror, and the Spitzer is only 2.8. No, or 2.8 foot. Now, how is it that when we look at this James Webb Telescope, remember I said that the diameter of the rocket determines how big we can actually make this, make this satellite? Well, it does determine it. But what happens is, when we look at the James Webb Telescope, we have to understand that it's got a faceted mirror. You see this? Separate mirror segments. And they fold up. And once it gets into space, it unfolds into the full-size mirror. It's really quite an elegant contraption, quite frankly. And I can't wait to see it in space, because a 21-foot mirror is going to give us resolution of planetary atmospheres far better than any we've ever seen. And there's a number of planetary candidates that are really close to us that are actually going to become very, very obvious for us to see with this telescope. I can't wait for it to happen. So, current estimates vary. This is true. But one of the things I wanted to say is there might be anywhere between 25 million, just like it says there, 25 million, or up to 10 to 20 billion planets like our Earth, just in our galaxy. And that means planets that are habitable in their habitable zone and just about Earth size. They could be a little bigger, a little smaller. And that's just in our galaxy alone. And oh, by the way, there's 2 trillion galaxies. So I think that's pretty impressive. Now, we're only getting started, all right? But I think that it's important. Go ahead. We only know one planet that does support life, and that's our own. Okay? And to understand how life might develop, we need to understand how it developed here. And to do that, I have a little bit of a. You can go back one actually. There you go. And to do that, I have something that might help us out. And I'm not sure I'm going to do this, but I have a little helper here, something that might help us figure out just how life developed here on this planet. And that's this roll of toilet paper. Now you might say, well, a roll of toilet paper, how can that possibly help us? Well, I can show you. I might need a little hand here, though, if someone can help me out. Can I ask Eric to help me out here? All right. Or wait, well, we have a guy, Jade. You're over there, right? Okay. All right, cool. All right. If you can just open that up, it's this little Velcro wrap on it. Okay. Now, this little helper, I'll take that. Okay, you can, good, that's fine. It's Velcro. It sticks to everything. It'll stick to you. It'll stick to everything. He had to wear a sweatshirt that had it's a perfect Velcro magnet, you know. So you'll see that there's paper on here. This paper comes out, and we start with something here, and it unrolls. Now this is 117 feet long, all right. And at 117 feet, okay. And let's start with you over on this side, okay. Go ahead on this side, all right. At 117 feet, yeah, don't fall. Yeah, you stop right there. Hold on. Okay. At 117 feet, okay, let's take a look here what this means. Okay, at this end, the Earth forms. This is sheet 298 out of 300. All right? Jade, I could use her on this side if you don't mind. Cool. I'm getting helpers from the audience, folks. Give me a little moment here. He's going to walk in front of the camera for a second. All right? And watch out for the cord there. All right, cool. And if you just hold that up. Now, if we look at this, we can see that here the Earth forms, right out here at the end. Then we have here the formation of the moon. This was 4.5 billion years ago. This was 4.6. This is 4.5 billion years. So now we come down a little more, all right? And let's pull it this way. There you go. That's exactly right. All right, and this is where the oldest Earth rocks were that we have been able to identify. It's 4.4 billion years ago. All right. Now we keep going. All right, and here, which is 4.2 billion years ago, okay? Let's get this down in the light. There we go. 4.2 billion years ago, we actually see the formation of the atmosphere. This is where the atmosphere began to form, 4.2 billion years ago. Now, what does that mean? It means that we had volcanoes spewing a lot of, you can actually just, okay, you can roll it if you want, but you can also just, if we just, there you go. Okay, good. All right. The atmosphere formed from the volcanic eruptions that were occurring, and we had a very, very heavy atmosphere. Remember I said the atmosphere was 90 times denser than it is today? Well, it was, and it's because of the volcanic eruptions that happened. So we keep going now, and we got to hope they can keep up with me now because we're going, because this is a long time. A lot of blank pages, you see, as we move forward throughout history, all right? And as we keep going, you okay back there? He's okay. He's hanging on there. Okay, good. You got the whole world in your hands, and in fact, some of the moon too. So now we keep going. Oh, here we go. Now we have something. And here about that. Look at this. Now we're at sheet 220. All right, and this is the early bacteria, the Cyanobacteria. These are the blue-green algae. These are the little guys that actually would eat the carbon dioxide and give back oxygen. That means oxygen is forming in our atmosphere for the first time, and that was a long time ago. So now we keep moving. All right, and you'll notice again a lot of space. Why is that? And yes, I drew all these lines on my roll of toilet paper. That means yes, I have no life. Okay, and I kept going and going and going, like the Energizer Bunny. Keep going and going, and now we see something. All right, now 2.7 billion years ago, this is when oxygen was starting to be recognizably built up in our atmosphere. Remember way back there when the cyanobacteria, those blue-green algae first formed? Those were the oxygen spewers. Okay, actually they were pooping oxygen, where we are breathing bacteria poop, just so you know. And that's kind of interesting. So if we keep going, and that was 2.7 billion years ago. Now we get up here to 2.5 billion years ago. This is called the Archean Era, and this is the Proterozoic life. That is to say, this is the earlier life, okay, on this planet, 2.5 billion years ago. Okay, we keep going, and we're moving now. I know we're wrapping it up again because it's outdoors, but usually when we do this, we unravel this in the entire space where we're actually doing the presentation, and this goes all the way around the auditorium, or the venue. I did it in Arkansas, and it surrounded the entire center section of 600 people. There was 600 overall, and the center section was completely encased with this as we walked around. It was a big auditorium. So we keep going now, past the Proterozoic times, and yes, lots going on, as you can see. A lot of nothing, it appears, but this whole time the Earth is percolating. It's creating life. More cyanobacteria, that is, those blue-green algae that are adding oxygen to the atmosphere. More of that's happening as we go. All right? And then we keep going. All right? I'm going slower because I don't want to overwhelm this guy here who's doing a great job keeping up, I must say. And now we come here. Okay, this is the formation of the early supercontinent, and it's called Rodinia. Okay? And this was 1.4 billion years ago. Look, we're still billions of years ago. See? All this time. So now we come up here and keep going. And now, finally, the first known animals. 1.2 billion years ago. First known animals. Okay? And we keep going. And I'm not being terribly detailed on those at this point because this could be an entire semester class. If this was a college class or any other kind of class, this would go on and on. All right? And now we have the breakup of the early supercontinent. Remember Rodinia? That happened back here 800 million years ago. Finally, we're in a few hundred million years, right? And so we keep going, and now we have to stop again because something else is happening. What's that? Well, we have the early multicellular organisms 700 million years ago. Okay? And we keep moving, and now look what we get. All right? We're now at a place where we have the early shelled organisms. That's 544 million years ago. And this is where the Cambrian Era begins. This is the point at which we start remembering our quote-unquote ancient history. All right? Look at all the stuff he's holding over there. A lot happened already on this planet, right? Now, if we just go a little farther, not too far. Okay, now the Cambrian Era ends 510 million years ago. And then we have the Ordovician Era, which starts, and that's early fish, which was around 490 million years ago. That's really interesting because that was early fish. Now, what do you mean fish? That means there were oceans. Yes, there were oceans that far back, obviously. And the oceans formed, and they had a salinity. Okay, they actually had a saltiness to them because sodium atoms, and chlorine atoms would combine in the water to make sodium chloride, which is salt. And you are also salty because we come from the ocean. And you contain the water in your tissues. All right? You have a vestigial ocean that you walk around with. You're like turtles, carrying a little bit of the ocean with you everywhere you go because that's where you were born from over time. You evolved from that. Interesting, right? And it's right there. It's all there for you to see. Now, if we look a little farther along, I said we have 480 million years ago, early fish. Well, then a little longer, we have the transition to land, and that was around 450 million years ago. The early land plants occurred, and that leads us from the Ordovician Era to the Silurian Era, 440 million years ago, and the Silurian Era ended 408 million years ago and start the Devonian period, when we see a lot of the large insects. Why the large insects? I always wondered why we always saw these large insects. Well, it happened to be because at that time, if you look at the levels of oxygen that were on the planet, those little bacteria buggers were doing a great job. Oxygen levels were far higher than they are today. Much higher. And so the insects could be much bigger. It was really, really interesting. Dinosaur insects. Yeah, dinosaur insects. Exactly right. That's right, Eric. So now the first insects, those were around 400 million years ago. Moving forward now, around 340 million years ago, we had the first reptiles. Aha. The first land mammals that were kind of the bridge between the sea and the land, reptiles, okay, amphibians, 340 million years ago. Now, I have to actually just come a little closer now because it's going to get a little bit tightened up. So now, back 280 million years ago, that's when Pangea formed, okay? Pangea formed 280 million years ago, all right? And Pangea, you remember, was basically a supercontinent, all right? Then about 245 million years ago, that's when the Triassic Era begins, okay? Then the Triassic ends, and we have the Jurassic beginning, which was 208 million years ago. You notice that we're not moving so fast through this anymore, are we? Things are starting to ramp up, okay? And now we have we have early birds and mammals 180 million years ago, all right? Now, then we get to a place where we have the early, I can't read my own writing, early flowering plants. That was very important because of pollen and insects. This is where the relationship between insects and plants sort of began, with pollination and cross-pollination. Very important. That was 150 million years ago. Then we had a few things, a few vacant years where not much was happening. But you see, things like biodiversity, changes in the local ecosystems where some creatures were more prominent, and growth of creatures and different strains and varieties of creatures happened. That variation occurred rapidly, and that was going on throughout here. Now, at 80 million years ago, the Rocky Mountains formed. That's just right here, okay? And then the Jurassic period ends. Now, we know what that means. That was 65 million years ago, and that was what we call an extinction level event. That's when an asteroid, known as a Florian asteroid, that came from our inner asteroid belt, we think, collided with the Earth off the Yucatan. At the time, it wasn't there, so to speak. It was, these plates have all migrated. And when it collided off the Yucatan, it actually created a dust pall, a cloud, which covered the sun for a period of years. And over time, the plant eaters lost their food, and the carnivores, which fed on the plant eaters, lost their food. And it started a domino effect where life died off. It was by far the lesser extinction event. The greatest one happened back there in the Permian era, which was back 500 million years ago or so. And this one here, this extinction event, is the one we know about. But I want you to understand and see how this extinction event worked, okay? So, but we'll see in a sec. Now, just 40 million years ago, India collided with Asia, all right? And that's what happened here. And we had a global cooling event starting to occur. Global cooling. We're actually in another global event. It might be sort of a cooling or warming. We're not even sure. And people say, well, increased carbon dioxide, it's all humans. You know what? If you look at the carbon dioxide levels, they're fluctuating all throughout history. And we can't tell whether we're responsible because 2 million years ago, they were doing this anyway. And they're still doing this. So why are we responsible now when we weren't way back here, when we didn't even exist? So you see, we're jumping the gun, in my view, on this whole climate change, global warming as our fault. Okay? That's my view. And certainly we contribute to it. I don't disagree with that. But we do have to take into account that when we look at the rest of the data, it's been doing this forever. Okay, forever and ever and ever. And this is something we have to pay attention to. So, now if we go back to, and this is kind of where it ends, and this is where Eric's gets a break because I take this off here. Now we get near the end. Okay, and I'm just going to cross over here for a second. I'd hate to turn my back, but I will for a second here. Now, as we cross over and look at this end, all right, just pull it back a little bit so I can just get a little stress on. There we go. Okay, so now we have, right here, we have, I mentioned here that India collides with Asia here 40 million years ago. And now, 23 million years ago is where the Tertiary and Cretaceous era, the Paleogene era, begins here. And this is the area at the time. This red line right here represents the time when there was the first ice at the poles. Okay? And this end, by the way, is us here tonight. Okay? But the first ice of the poles is within a finger's length here. Okay? So that's pretty interesting. Now, what's further interesting is if you look at this line right here, this is Lucy, 4.4 million years ago. Australopithecus afarensis. This is the first bipedal hominid at the time. Now, whether we come from that or not, okay, it is the first bipedal hominid, all right? And Lucy caused quite a stir, and this is where it is. and this is the end. Okay, right here. It's not all the way at the end here. It's this line is the end right here. That's the end, and Lucy's right there. So you can see that what we consider dinosaurs, for instance, which died out right over here, okay, that's recent history. It's not ancient history. Look at, just step into the light for just a minute. Come forward and just come and show that, let that thing hit the light so you can see. Look how much history has passed on this planet. All right? And this is the only thing that we pay attention to as what we call significant. I'm sorry, folks. Okay, this is recent history. The whole history of the planet is this. And now the whole point of this exercise, and thank you for that, the whole point of this exercise is, if you just roll it up and just, yeah, that's it. The whole point of this exercise is to show you how the development of life here is something that is that is something that takes a lot of time, but could something develop elsewhere and around an exoplanet the same way as here? Absolutely. But could we get humans there? Well, you know, if the dinosaurs didn't get extincted, as I joke with and say that joke word, it doesn't exist. If it's extincted life, like if the dinosaurs didn't die, would we see the same thing? Maybe not. Maybe not. But if we're going to look for life, one of the ways we're going to do it is we're going to have to try and find out if they're here. And to figure out if they're here, we're trying to find the elusive smoking gun. And it's not the blue screen of death. Okay. All right. If we go to the next one, okay, it's something we call UFOTOG 2. Now, UFOTOG 2 is the name of a UFO, or aerial anomaly detection system, that we've created. It's actually a system by which we want to try to deduce in a scientific manner whether aliens are here. And if they're here, well, then there should be a scientific way to show it, right? So there's a lot of stuff ufology suffers from. There's a whole bunch of stuff. There's lack of high-definition photos. Research programs are not really funded well. Poor quality evidence. And hoaxers use really good CG technology and so forth. We're facing a lot of issues trying to get good data. All right. Well, UFOTOG 2 is something that can challenge that because we're using a special system that has on each platter multiple instruments that aren't prejudiced, that aren't biased, to look at a single sighting and make a determination in the infrared, in the ultraviolet. You know, did the magnetic field change? Has the local gravity field changed? Is there an EMF, that is an electromotive force? Have there been any currents generated by something that happened here? Do we see gamma rays coming from this object? All of these things tell us a different story about the nature of the object we're seeing in the sky. If we're seeing a satellite, we're not going to see any of the aforementioned things. If it's an aircraft, we're not going to see any of the aforementioned things. If it's an unidentified flying object using advanced alien propulsion, advanced propulsion that we tend to think might resist or exist in the string theory arena, then maybe we'll see some of these things. And what this is a scientific way to figure that out. All right. So the genesis of UFOTOG is really simple. It was started by visual effects legend Douglas Trumbull. Doug is an Academy Award-winning guy. And I met him several years ago, and he's a very industrious person. He's also a UFO hunter. I was doing an NPR show on a National Public Radio show, and we were talking about X-Files and UFOs. And the host said to me, I got to get you on a show with Douglas Trumbull. And I went, what? Doug Trumbull? And I started to shake because this is a man who I've admired. I'm in the movie arena. I actually make visual effects models. Same type of thing that Doug does and has done for decades. And I'm like, wow, I modeled some of the stuff I do after his work, and I used his techniques. And so when I got home, I immediately wrote him an email. I found his email online when I heard about this thing called UFOTOG that he created. And this is the original UFOTOG. And he said, he actually wrote back within an hour and said, wow, I went to your website. It's excellent. I could use you right now. We're doing a commercial that could use you. What? And now I started to really shake because now I was going to meet the person of whom I had dreamt I could meet someday and just dismissed it as silly to even think so. Next thing you know, I was there working on these things, and we've been friends for the last 6 years. Absolutely amazing stuff. So now UFOTOG is a system by which they could track UFOs, the original UFOTOG, using a Humvee. And it had these telescopes sticking out of the top that would track and find any objects, anomalous objects in the sky, and track them automatically. And we won't worry about this. This just gives a list of the instrumentation that's on the UFOTOG system. All right. And we're using this in a new way, okay? If you notice at the top, it says UFOTOG 2. The original UFOTOG used a number of these items here, but UFOTOG originally was a single large Humvee with instrumentation that was very heavy, very costly. When Doug and I got together, we talked about making this smaller. And now we're talking about something that's only about 2 feet in diameter at most. And it's just covered with instrumentation that would actually be able to see all these things in a different way. We have cameras in SkyTour LiveStream at the John Zach Memorial Observatory, where we do the SkyTour LiveStream. That camera that we use uses a chip that we want to use in our UFOTOG 2 system. We've renamed UFOTOG 2 to the Aerial Anomaly Detection System because that is something that's a little more palatable to people that want to invest in the system. The word UFO tends to scare people away, but we're actually trying to get at the truth. But the system itself can look for meteors, it can look for errant asteroids. It's actually something that can actually benefit science in a number of ways. And they never have to mention the word UFO. We'll do that. We'll do that in the background. So UFOTOG 2 is something that's going to be laid out in triads. It's a triangular layout. They're about a half mile to a mile apart each. Why? So that when a unit here covered with 5 or 6 instruments, and a unit here covered with 5 or 6 instruments, and a unit here with the same, if this one sees one with 4 or 5 of its instruments, and this one sees the same thing, they can triangulate. And the data from one can be shared with the data from another, and together we have 5 observations here and 5 observations of the same object here. That means 10 observations of the same thing in the sky, whereas before we had one cell phone. I got this picture, I saw this thing in the sky, and of course it's like this. It's going all over the place because that's how people film things when they're excited. They can't just stand still. You know how it is. If they capture an explosion, whoa, and they shake. Nothing works. It's not good. So that said, I think that UFOTOG 2 is subjective. There's no, boom. It's subjective. There's absolutely no prejudice, one way or the other. No bias. They're just objective instruments looking at these things in the sky. And that's what we do. That's what we're going to do. So we use different methodologies. You can read this at your leisure, different radios and so forth. And to actually get the signal from the UFOTOG to our cell phones in an instant, well, what we do is we have a system on there. And that system is called the SPOT. What is SPOT? Well, SPOT is a GPS bounce transmitter system. We actually can bounce our signals off of GPS satellites and get the information back to our phones in our pockets the instant it happens, no matter where we are on planet Earth. So if these are deployed across the ocean or in the ocean, we have a subsea one too that looks down for unidentified submerged objects, as well as look up for unidentified flying objects. Okay, then we'll see that the signal will come through and get us on our phones, and then in later phases we'll be able to actually download the data directly from the unit by logging into it and going to its quote-unquote website, because we'll have a little server on it and we'll be able to get to the data. So that's neat. We can skip this. I kind of already talked about that. But here's the units. The UFOTOG unit is composed of these cameras, which you see the blue, and there's 7 of them with one on the top. Solar panels, these have since been located off the unit and on a pole. And part of the reason is because the energy budget, as we started to design this, the energy budget started to get bigger. So take the power right off, make the panel a little bit bigger. Maybe it's going to be a 2-foot by 2-foot panel, okay? And it's going to be on a pole. Why? We didn't want to put it on the ground. And the reason for that is because, well, okay, I'll say it. I don't want to get an alert saying, Unit 5A-6 out in the Phoenix Desert caught something. And then we log in and we see a picture of a coyote peeing on our unit. Because it'll be on the ground, and that's a bad thing. So we're going to put it on a pole where it's higher in the air, and I think that's going to be great. That'll be much better for us, and it'll also prevent thievery. It'll prevent people from going after it if the pole is high enough into the air. And that'll prevent a lot of things. It'll help us greatly. It'll isolate it from the ground, where we also get other issues like with nearby thunderstorms. They're going to send a ground current through the ground if the lightning strikes the ground. If it strikes our pole, well, we're out of luck, okay? But the fact is, the lightning will probably not strike our pole, you know, that kind of thing. But if it does, it does. So the UFOTOG system has these cameras on it. Okay, and then down below, okay, those are the multispectral cameras. Okay, and then up top we have the solar trickle charging, which we already just said is going to be off the unit. Now we have the spot transmitter. This is that thing which generates the signal that goes to our GPS satellite. We've modified the messages to the GPS satellite. They'll be able to take the GPS satellite image or data and modify it and bring it down to us. And I want to thank you gentlemen, Eric and Jade, who actually in the background rolled up that big toilet paper roll once again in reverse from when I totally... Yeah, right. He did 4.6 billion years worth. I mean, that's heavy work. Okay, so we have the spot transmitter that's going to get us our data, okay? And then we have a cellular antenna. Why? Well, because we want to be able to call the units from time to time and do a diagnostic test. So maybe we can get the diagnostic information out of them. Okay, so it's very important. Now on the other side, we have this gamma ray detector that we already have. We're just miniaturizing it. And here's another little secret for you: your iPhone can detect gamma rays. Do you know that? All you have to do is cover the camera and download the gamma ray application. No, we're not going to put iPhones on these, okay? We're going to use something a little bit more sophisticated. But you see, some of this technology is actually getting within reach of us, every one of us, in some fashion or another. And I think that's really important to understand. And so all you have to do is apply this to what we're doing. So we have leveling legs, which when it's on a pole, it may or may not be suitable. Depends on how big the pole is. But we have batteries in the center. Okay, next. And then we want to actually see MUFON become part of this. And I've talked to our fearless leader, Jan Harzan, about this, and he thinks it's a great idea. And Jan says that we can use the Mutual UFO Network people on the ground. We have field investigators in every state and in countries around the world. And some of these field investigators are very qualified people, and if they're not, we'll teach them. And they will create and maintain, well, they'll maintain our units that we'll send to different states as we make these units. So we're working on it, and we think that we're going to come a long way. So hopefully, everything you just saw for the last however long this was, okay, oh, that's fine. We're done. Yeah. Well, first of all, let me just say this. Let me just say, I want to thank you guys for listening. And those of you out there in the stream, if you have questions, I'll be happy to take them now. And right now, we'll take a question from Bill's mother. Oh, she's being very sweet to me. Thank you very much. She's thanking me for showing everything to you, and I well, thank you so much. Thank you. Thank you very much.
Okay, so Mark is wrapping up, and I definitely want to thank Mark for everything he's done as well.
Thank you, guys. Thank you very much.
And we're going to take some questions from the chat, and Amanda's relaying them to me on Skype right now.
Awesome.
I just want to know, Amanda, if you can hear me right now. Just let me know on Skype. It sounds like I'm a bit loud. So
from out here.
Yeah, so Keith is gonna go. I'm way too loud. Okay, we're gonna fix that. Keith is gonna go in and fix that.
Can I ask a question while you're doing that?
Yeah, Ronald wants to ask a question. Go ahead.
Yeah, I had someone want to ask a question about James Webb.
Yeah.
Are they going to use that to research for NEO? NEO? I don't know.
Oh, you mean near-Earth objects?
Yeah.
You know what? It's probably going to be tasked for some of that. Now, the
Keith,
James
stand
Webb
by.
Telescope
I'm too loud.
The James Webb Telescope is a system that's actually
Channel 4
going to have a lot of infrared systems on it. It's actually going to be basically an infrared telescope. So NEOs, or near-Earth objects, will be a perfect target for the James Webb Telescope. But the James Webb is also going to be good because it's going to be out at a Lagrange point where it's going to kind of float far away from the planet. It's going to be able to see the atmospheres of these exoplanets. And with a 21-foot mirror, it's by far the biggest space telescope ever launched by any country. And it's going to be a miraculous instrument once it's in space.
Okay, Mark, we're going to do another check on this mic here so
Sure
we can
thing.
ask some questions. And Keith and Amanda, let me know. Just let me know how the sound is.
It's like live television, things go
There you
right,
go.
things go
and
wrong.
I just put this mic so we can get the questions in coming from
Yeah.
chat.
I want to
All
thank
right,
you.
Amanda says it's better now.
Okay.
I got a question for you.
Okay, Bill New York Skywatcher has a question.
You
Go for
mentioned
it.
earlier about exoplanets
Yes.
and some of these super hot or super cold in the extremes.
Yeah.
How is it that we have the moons that are sustainable for possibility of life under those conditions?
That's an interesting question because one of the exoplanets that we found out there is actually one that's too large and too inhospitable, let's say, for life as we know it. Okay, it's a gas giant like a Jupiter, but it may have a number of moons around it. And just like our Jovian planets, like Jupiter and Saturn and Uranus, okay, and Neptune. And if it has enough moons, some of those moons might be habitable. And those might actually have life. Now you might say, well, wait, how could that possibly be? I can tell you. If you look at Saturn, Saturn has a moon called Titan. Titan is nearly planet-sized. And it actually has a set of conditions that are totally inhospitable for us because they're too far away from the sun. But just imagine if Saturn was in the habitable zone. Titan would be a lot warmer, wouldn't it? And it might have evolved into a life-bearing planet, even though it's just a moon. So just imagine like tonight, it's a beautiful night, and we look up in the sky, and we see Saturn with its rings. And we're just on Titan, and we just evolved into that life, into that moon's capability, for harboring life. That's something that's pretty amazing to me. And I think that if we look at planets that are Jovian moons in some of these systems, if the Jovian planet actually is in the habitable zone of the star, we have to consider, and the James Webb could probably help us with this, we have to consider that some of the moons of that planet might actually be life-bearing, like life possible. Consider Europa around Jupiter. What would happen to Jupiter if it was in the habitable zone? Would Europa be life-bearing? What would happen to the icy crust on Europa? We don't know. Maybe it'll actually be something that could harbor life for us and whatever. But we don't know. Maybe Europa would have had an atmosphere or a semblance of an atmosphere. Maybe little Enceladus, only 300 miles across around Saturn, might actually have been something that might have held possibilities of an ocean, like a small ocean planet. There's a lot of possibilities here.
Okay, BRD166 asks, as the sun burns out, could life similar to Earth develop on Venus?
Well, we just went through that whole thing, and if life develops in a way that's similar to what we just saw for this long toilet paper thing that I did right here, okay, then, and very nicely folded up, guys. Thank you so much for rolling it up. If life develops in a similar pattern as here, then when the sun actually starts to contract as it gets older and starts to run out of hydrogen, another thing's going to happen that's going to remove any possibility for having life on Venus, or the Earth for that matter, because after it starts to contract from running out of hydrogen fuel, it's going to get that hydrogen that's in the outer envelope closer to the center. And when that happens, fusion's going to begin again. But it's going to be in this shell around the outside of the core that was actually creating this energy of the star originally. And that's going to make an even bigger star. And the star is going to expand into this giant red star called a red giant. And when it does that, it's going to swallow Venus internally and destroy it and the Earth, most likely. So I don't think that'll happen.
Okay, the next question is from Lorraine, and she wants to know, when did some species crawl back into the ocean like the whales?
Well, it's possible that those never left the ocean. But there's also possibilities when we look at some of the bone structure of some of these sea creatures, it looks as if they had articulated hands and fingers. It looks like there's thumbs on some of the fins of these creatures. So that's possible that maybe the creatures did go back. I can't say the exact time at which this happened. That's more for paleontologists to discuss that. But I can say that there are possibilities that some creatures that maybe came onto the land might have gone back to the ocean in the past. But there are certainly some that formed in the ocean and never left the ocean. And that's another thing. So I'm not sure which species may have done that. But that is a very good question, Lorraine. Thank you.
And Darryl was just joking. And
who was?
Does Mark reuse his toilet paper?
I was. But as I said, I actually used real toilet paper to do this in the beginning. But after 2 or 3 usages, the toilet paper started looking somewhat ratty. And people said, "Is that used toilet paper?" And I had to answer, "Well, yes, it is." And that kind of raised people's hackles a bit, and they ended up not wanting to touch it when I was walking around. And I said to say, "Well, no, it's used," and I was actually using it as in using it for the presentation, not any other way.
Ronald, is there any question coming in from your Facebook?
Oh, no, I think I asked one that I had.
Okay. Now I'll ask. There's no more questions coming in right now from your chat room, but I'll ask another. In your estimation, best guesstimate, how many exoplanets do you think are out there in our Milky Way?
The actual estimates vary. It depends on which analysis you look at. But there could be, and I had a slide showing the rough estimates, but if we look at the low end, there might be as few now as 20 million. Okay? And that's Earth-like planets. There's many more than that anyway. Okay? But as few as 20 million Earth-like planets in our Milky Way. All right? And as many as 40 billion, depending on how many stars we actually have in our Milky Way. We don't even know how many stars we have in our Milky Way. And you say, well, how could we not know that? It's easy. When you go to look through the center of our Milky Way, you can't actually and try to get an estimate of the star counts in our Milky Way. And we don't even know. It's between 100 billion and 400 billion stars.
Okay, there are a couple of more questions from Ted coming in from chat from Amanda, but Jade has a question first.
Yeah, my question is the useful tog.
Tog, yeah.
Would that eventually be made that you can buy that on the market in a civilian area eventually?
Yeah, it's a civilian project. And the thing about our data, and thank you, Jade, for asking that question, because I did forget to mention this one very important point. When we acquire the data with this aerial anomaly detection system, formerly known as UFOTOG2, when we acquire the data, we believe that data belongs to everybody. We don't want to hoard the data. We're not going to create this data and make it our own. Yes, he's waving his hand, yay. Yeah, that's right. I mean, because this is our project, humanity's project. It's not my project. It's not me and Doug. It's not, me and Doug and a bunch of other people that are going to just hoard this data and keep it and only give it out if you subscribe. No. This is humanity's data. And we want to try and make that point. It's very important to make that point.
There's actually a question coming in from Ronald's Facebook. Ulfi wants to know, do you think aliens have inspired you to do this work?
I can tell you this. In a sense, yes. I think that the potential existence of an advanced race out there, I mean, it's clear night tonight. When I look up, I see stars over my head, and I can't help but think that there might be something else out there, some other life form up there that might be, looking back at me saying, gee, I wonder who else is up there, or out there. So yes, in a sense, yes. I have been inspired by the possibility of alien life. Absolutely.
A couple more questions.
Yeah.
And this is from your chat room on YouTube.
Okay.
Ted asks, if we can inhabit a moon, what happens when it goes behind the planet and away from the sun?
Awesome question. I'm so glad you asked that, Ted. That actually shows, this shows you, man, the SkyTour LiveStream folks, they listen and they pay attention. We've talked about this before without actually explicitly mentioning it, and Ted actually brought this up, and I love it. Thank you very much, Ted. That's a good question. The answer is, when it goes behind the planet, and because the planets and the moons do tend to rotate and orbit within the plane of the solar system, it is possible that when they go behind the planet, that there will be several hours, because it's only going to be hours, not years or days. It's going to be a few hours that it goes behind the planet. It'll be a few hours when the entire planet is in darkness, all right, or moon, all right, and then as it comes back out, it'll be thrust into the light again. And if it's close enough to the larger planet, then it might also be tidally locked, where it only has one face facing it like the moon faces us. So there's a lot of complex dynamics there in a potential orbital system like that. But the answer about whether life can exist is that it's still possible, I think, for life to exist, because Ian Malcolm, played by Jeff Goldblum in Jurassic Park, said famously a line that I'll never forget. When they said, no, we don't engineer these dinosaurs to be able to reproduce, and he says, life will find a way. And it's true, life will find a way. We see that in nature. Look at the microbes that exist in hot geysers that would scald the skin right off our bodies. So we do have that possibility, and I think that life might find a way in such a situation. Yeah.
One final question.
Yes.
Tana wants to know.
Hi, Tana.
What are your thoughts on the multiverse theory?
Well, there's a lot of theories about the multiverse. First, let's define what the multiverse is. When the Big Bang occurred, there was a certain amount of mass that created this primordial superatom explosion that occurred to create our universe. That's the evidence we see. However, when we also look at the evidence, we see that there wasn't enough mass to create a universe of this size. It's missing some mass. At least that was some of the theory. And so we talked about missing mass being as a possibility, that missing mass was actually created in other universes that were spawned along with our own. So there is a theory that multiple universes were spawned at the Big Bang, and not just one. And that would help explain the missing mass. Since then, we've actually found a lot of other possibilities and a lot of other locations where mass could be hiding. We also found an interesting finding we've talked about in the past on SkyTour LiveStream. We've also talked about the fact that there's a lot of dark matter in the universe and a lot of potentially a dark energy. Now, what's dark mean? Black? No. Dark just means unknown. We don't know. So unknown mass, unknown energy. That's something that is a very strong possibility still, but we're thinking that the concept of dark energy might not need to be employed anymore. Now, dark energy could go away. What's dark energy? Well, when we see that the universe is expanding outward, some of the earlier findings showed that it wasn't just expanding outward. It was actually accelerating as it went outward, as if a balloon in a vacuum chamber existed. That is to say, the balloon being the universe and the vacuum chamber being what's outside the universe. As the air is pulled out of that vacuum chamber in real life, in our life, you would actually see the balloon start to expand, and if you accelerated the removal of the air, that would expand outward. In other words, the walls of the balloon would be pulled outward faster because of the vacuum in there. Now, of course, the pressure inside the balloon would be pushing outward, and that would cause the expansion to accelerate as well. But they were trying to liken it to a force outside the universe that was like negative mass, actually, that was pulling the outer edge of the universe outward. But since then, they've noticed that there are some areas where the universe might actually be moving a little bit differently than they thought. And that possibility of dark energy could actually be an early concept that gets discarded in the future. But dark matter still exists, and dark matter is something that we need to consider, that mass, that extra mass that we need. So the universe is a complex place.
Amanda wants to know, what exoplanet would you most like to explore for life, and why?
Any of the ones that are super habitable. No, that means planets that aren't like the Earth. It means that planets that are better than the Earth. And, boy, that's a hard one for people to swallow, that they're not on the best planet for life. But the fact is, and I say any, Amanda, because of the fact that there is no one planet that I would like to go to. All right? There are a number of planets out there that are absolutely wonderful targets. And you and I have actually talked about them. And those of you who have heard of Amanda, you know that Amanda Curran is actually the SkyTour LiveStream co-host, and she's also the SkyTour Radio co-host. And you can listen to her and I on SkyTour Radio every Sunday night at 9 p.m. on kgraradio.com.
One final question, because probably the camera's going to die any second anyway. This is from Dave Schock.
Dave Schock. Hey, man, what's happening? Dave Schock.
Yes.
Just want to mention, Dave Schock, the guy that is the curator for CubeSat, the other possibility for looking for alien life and possibilities of extraterrestrial influence on our planet. He's masterminding the CubeSat project to launch into space these small satellites to be able to do that observation from above. I want to congratulate Dave Schock on that, and keep it going, man. Keep it going. Go ahead.
Dave wants to know, if looking at a star and its exoplanets, are we seeing the light from it at light speed, plus the speed of the sun is coming at us, or how is the speed affect what we see?
This goes into something that we call reference frames, if I understand his question correctly. The speed of light in the universe is the speed limit in our universe. There's nothing faster than the speed of light. All right, so we don't have any way to say that anything is the speed of light plus 500 kilometers a second or something. It's always going to be the speed of light, and I know that's sort of hard to understand because if you were on a ship traveling near the speed of light and you shined a flashlight, all right, if you're in that ship, the flashlight would hit the wall instantaneously, and you say, "Hey, that's twice the speed of light." Not so, because someone watching that ship from another location going by would see the light beam frozen and not moving, okay, if you were moving at light speed. No one can move at light speed, okay, but that has to do with something called reference frame, so no, it's always the speed of light.
All right, we're going to try to squeeze two quick ones.
Really? The final question before the final question, and then the final question followed by the final question. Welcome to Bill's place, ladies and gentlemen. Bill New York Skywatcher.
Ted wants to know, any chance Earth will regain the high oxygen content?
As a matter of fact, no. I can't say for sure. I can't predict the future, but I can say this. Scientific study has shown that the oxygen levels on this planet do fluctuate, and right now there's a study that's showing that the oxygen levels on our planet are depleting, going down. So that could be a natural occurrence. It could be due to the population on the planet. It could be due to other factors. It could be due to plankton in the ocean, which are 50% of the oxygen generators on this planet. It could be due to the forest on our planet, which are the other 50% of the oxygen generators on this planet. So we don't know. But as far as getting more oxygen, I think we're going the other way. I think it's going to be depleted more than replenished.
And finally, from Tana, Mark, do you think we're more likely to find a life-friendly planet or a moon first?
Ooh, that's a good question. I would guess we're going to find a life-friendly planet, Tana, and the reason for that, and I want to thank you all for your attendance and questions. Thank you so much. The reason for that we probably find a life-bearing planet first is because it's easier to find planets now than moons. Super distant in the future, we're probably going to be able to find moons like no tomorrow, in the same category, in the same frequency we find planets. But we're not able to do that yet. So we're going to probably find planets that are life-bearing.
And I just want to quickly mention, tomorrow there's going to be another special presentation live from the Cup and Saucer Diner in Pine Bush, New York.
That's right.
Mark D'Antonio and Commander Cobra, host of Task Force Griffin, 3 p.m. approximately tomorrow Eastern Time. We're going to do a live show, and Keith Ickes, and hopefully we're going to get Paul as well as their guests. So make sure to tune in. Now, tomorrow it's going to be KGRA DB YouTube. So you need to check that out. And hopefully maybe tomorrow night we'll be back on SkyTour LiveStream as well. And I want to thank Amanda for everything she does and all her help.
And I want to thank you, Amanda, as well. Thank you very much, Amanda, for all your help.
Any last words, Mike, before we wrap?
Good night.
There you go, everybody.
Thank you, guys.
Have a great night, everybody. We're going to call it.
All right, we're going to see you again.
Good night, everybody.
Good night.